Hi everyone, and welcome back to the channel. In the last video, we covered the broad definition of AI and the hardware behind the technology. In today's video, we are going to discuss a brief history of AI from the 21st century onwards, the top current companies contributing to today's expansive AI landscape, and the myriad of software capabilities powering AI's innovation to close things off. In the early 2000s, several researchers became concerned that mainstream AI was too focused on measurable performance in specific applications known as narrow AI, and had abandoned AI's original goal of creating versatile, fully intelligent machines. In 2008, Goertzel adopted the term artificial general intelligence for the new subfield, founding a journal and holding several conferences which caused the new field to grow rapidly, buoyed by the continued success of artificial neural networks and the hope that it was the key to AGI. Several competing companies, laboratories, and foundations were founded to develop AGI in the 2010s. DeepMind was founded in 2010 by three English scientists, Demis Hassabis, Shane Legg, and Mustafa Suleyman, with funding from Peter Thiel and later Elon Musk. The founders and financiers were deeply concerned about AI safety and the existential risk of AI, and Musk was among those who was actively raising the alarm. In 2012, Geoffrey Hinton, who had been leading neural network research since the 80s, was approached by Baidu, which wanted to hire him and all his students for an enormous sum of money. Hinton decided to hold an auction, and at a Lake Tahoe AI conference, they sold themselves to Google for a price of $44 million. Hassabis took notice and sold DeepMind to Google in 2014, on the condition that it would not accept military contracts and would be overseen by an ethics board. Larry Page of Google, unlike Musk and Hassabis, was an optimist about the future of AI. Musk and Page became embroiled in an argument about the risk of AGI at Musk's 2015 birthday, and they had been friends for decades but stopped speaking to each other shortly afterwards. Musk attended the one and only meeting of the DeepMind's ethics board where it became clear that Google was uninterested in mitigating the harm of AGI. Frustrated by his lack of influence, he founded OpenAI in 2015, enlisting Sam Altman to run it and hiring top scientists. OpenAI began as a nonprofit, free from the economic incentives that were driving Google and other corporations. However, Musk became frustrated again and left the company in 2018. And as a result, OpenAI turned to Microsoft for continued financial support, and Altman and OpenAI formed a for-profit version of the company worth more than $1 billion in financing. Following Musk's steps, in 2021, Dario Amodei and 14 other scientists also left OpenAI over concerns that the company was putting profits above safety. They formed Anthropic, which soon had $6 billion in financing from Microsoft and Google. Rewind back to 2017 when the AI boom started with the initial development of key architectures and algorithms such as the transformer architecture that was proposed by Google researchers, leading to the scaling and development of large language models exhibiting human-like traits of knowledge, attention, and creativity. Large language models based on the transformer were developed by AGI companies, and OpenAI released ChatGPT 3 in 2020 and DeepMind released Gato in 2022. These are foundation models as they are trained on vast quantities of unlabeled data and can be adapted to a wide range of downstream tasks. These models can discuss a huge number of topics and display general knowledge. Even Bill Gates was skeptical of the new technology and the hype that surrounded AGI. However, Altman presented him with a live demo of ChatGPT 4 passing an advanced biology test, and Gates was convinced. In 2023, Microsoft Research tested the model with a large variety of tasks, and concluded it could reasonably be viewed as an early, yet still incomplete version of an artificial general intelligence system. In 2024, OpenAI O3, a type of advanced reasoning model developed by OpenAI, was announced. On the Abstraction and Reasoning Corpus for Artificial General Intelligence benchmark, developed by François Chollet in 2019, the model achieved an unofficial score of 87.5% on the semi-private test, surpassing the typical human score of 84%. Investment in AI grew exponentially after 2020, with venture capital funding for generative AI companies increasing dramatically. Total AI investments rose from $18 billion in 2014 to $119 billion in 2021, with generative AI accounting for approximately 30% of investments by 2023. According to metrics from 2017 to 2021, the United States outranked the rest of the world in terms of venture capital funding, number of startups, and AI patents granted. OpenAI's valuation reached $86 billion by early 2024, while Nvidia's market capitalization surpassed $3.3 trillion by mid-2024, making it the world's largest company by market cap as the demand for AI-capable GPUs surged. Circling back to OpenAI, ChatGPT was launched on November 30th, 2022, marking a pivotal moment in artificial intelligence public adoption. Within days of its release, it went viral, gaining over 100 million users in 2 months and becoming the fastest-growing consumer software application in history. ChatGPT's success prompted unprecedented responses from major technology companies, as Google declared a code red and rapidly launched Gemini, formerly known as Google Bard, while Microsoft incorporated the technology into Bing Chat. The rapid adoption of these AI technologies sparked intense debate about their implications. In March 2023, over 20,000 signatures, including computer scientist Yoshua Bengio, Elon Musk, and Apple co-founder Steve Wozniak, signed an open letter calling for a pause in advanced AI development, citing profound risks to society and humanity. By mid-2024, however, the financial sector began to scrutinize AI companies more closely, particularly questioning their capacity to produce a return on investment commensurate with their massive valuations. Some prominent investors raised concerns about market expectations becoming disconnected from fundamental business realities. Jeffrey Gundlach, CEO of Double Line Capital, explicitly compared the AI boom to the dot-com bubble of the late 1990s, suggesting that investor enthusiasm might be outpacing realistic near-term capabilities and revenue potential. These concerns were amplified by the substantial market capitalization of AI-focused companies, many of which had yet to demonstrate sustainable profitability models. In January 2025, OpenAI announced a new AI, ChatGPT-Gov, which would be specifically designed for US government agencies to use securely. OpenAI said that agencies could utilize ChatGPT-Gov on a Microsoft Azure cloud or Azure Government Cloud, on top of Microsoft Azure's OpenAI service. OpenAI's announcement stated that self-hosting ChatGPT-Gov enables agencies to more easily manage their own security, privacy, and compliance requirements, such as stringent cybersecurity frameworks. And lastly, in January 2025, a significant development in AI infrastructure investment occurred with the formation of Stargate LLC. The joint venture, created by OpenAI, SoftBank, Oracle, and MGX, announced plans to invest $500 billion in AI infrastructure across the United States by 2029. The venture was formally announced by US President Donald Trump on January 21, 2025, with SoftBank CEO Masayoshi Son appointed as chairman. Shifting gears, the top 10 companies in the AI landscape today include Microsoft, Nvidia, Alphabet, Amazon, Meta, Taiwan Semiconductor Manufacturing, ASML Holding, Adobe, International Business Machines Corporation, and Arista Networks. Let's start with Microsoft, that has invested nearly $14 billion in OpenAI and has integrated ChatGPT into its Bing search engine. Microsoft has also combined all its AI co-pilots into a single AI experience called Microsoft Copilot. In fiscal 2025, Microsoft plans to invest $80 billion on AI-enabled data centers to train AI models. Next up is high-end chipmaker Nvidia, that provides massive processing power needed to run advanced AI applications. Nvidia has been one of the best performing stocks in the entire market in recent years, and it's largely due to the company's AI exposure. Orders for Nvidia's H20 chips have reportedly surged in China, and companies push to adopt DeepSeek's AI models. Third is Google and YouTube's parent company, Alphabet, which uses AI and automation in virtually every facet of its business, from ad pricing to content promotion to Gmail spam filters. Google launched its Bard AI chatbot in March 2023 and its Gemini generative AI model in December 2023. Alphabet raised some concern within the AI community in February when the company lifted its ban on using AI technology to develop weapons and surveillance tools, but overall, Google is heavily investing in Gemini model and integrating it throughout its product stacks. This next company is probably well known to a little too many people, as they've probably impulsively bought some products at 3 a.m. in the morning. Amazon has integrated AI into every aspect of its business, including its targeted advertisements, its marketplace search, recommendation algorithms, and Amazon Web Services, or AWS. Amazon offers a wide range of AI and machine learning services to its AWS cloud customers, including advanced text analytics, automated code reviews, and chatbots. In February, Amazon announced Alexa Plus, a revamped version of its Alexa personal assistant that uses AI technology to be smarter, more conversational, and more capable than previous Alexa versions. Next up is Meta Platforms, which is a market leader in social media and online advertising, and is the parent company of Facebook, Instagram, and other platforms. CEO Mark Zuckerberg has adopted a bold strategy of making Meta's AI technology free and open to the public in an effort to gain market share and drive down competitors' prices. Meta is reportedly in talks to build a new $200 billion data center campus for its future AI projects. While Meta's AI costs are spiking, the company's overall profitability is still improving. A company we discussed at length in the last video is Taiwan Semiconductor Manufacturing, which is the world's largest pure-play semiconductor foundry. TSMC manufactures all the advanced AI semiconductors for Nvidia and other AI chip makers. In December, it was reported that TSMC is in talks with Nvidia to manufacture Nvidia's Blackwell AI chips at TSMC's new plant in Arizona. Although Taiwan Semi may get hit by new semiconductor export restrictions, AI investments, receding inflation, and a rebound in electronic device demand will support ongoing growth. TSMC is also expected to begin Apple chip production in Arizona soon. The seventh major player in today's AI economy is ASML, which produces photolithography systems and other processing equipment used in semiconductor fabrication. ASML is the only major producer of the extreme ultraviolet lithography equipment necessary to produce advanced AI chips. Taiwan Semiconductor and Samsung Electronics are two of ASML's largest customers. Adobe, the eighth company on the list, produces creative content software and other applications used for marketing and e-commerce. The company's Firefly generative machine learning model is generating customer interest across Photoshop, Illustrator, and other platforms. Adobe has also applied its Sensei AI and machine learning technology to its Adobe Analytics, Campaign, and Target products. Adobe's newest batch of generative AI tools include Firefly Bulk Create, an app that allows users to resize or replace the backgrounds of up to 10,000 images in a single click. Ninth on the list is IBM, one of the biggest technology companies in the world today. IBM has been developing ways to adapt its AI supercomputer Watson to revolutionize healthcare, finance, law, and academia. IBM's portfolio of Watson AI solutions includes applications to improve customer service, automate workflow processes, and predict outcomes. IBM's Watson Studio even helps enterprise customers build AI applications. And in December, IBM announced a collaboration with defense intelligence company Janes that will integrate open source defense and security intelligence data into IBM's Watson AI and data platform. Last but not least is Arista Networks, which supplies cloud networking solutions to internet companies, cloud service providers, and enterprise data centers. Arista's high-performance cloud networking solution and high-throughput data center switches are necessary to provide the processing power required for intensive AI workloads. In the second half of today's video, we will be covering the software that is used to power AI. Software refers to a set of instructions which enable the hardware to perform a specific set of tasks. Examples of AI software include machine learning, deep learning, neural networks, natural language processing, large language models, generative AI, and agentic AI. We'll split each of these topics up into 3 sections. The easiest way to think about AI software's machine learning, deep learning, and neural networks is to think of them as a series of AI systems from largest to smallest, each encompassing the next. AI is the overarching system. Machine learning is a subset of AI. Deep learning is a subfield of machine learning, and neural networks make up the backbone of deep learning algorithms. It's the number of node layers, or depth, of neural networks that distinguishes a single neural network from a deep learning algorithm, which must have more than 3. An increasing number of businesses, about 35% globally, are using AI, and another 42% are exploring the technology. Your AI must be trustworthy because anything less means risking damage to your company's reputation and bringing regulatory fines. Misleading models and those containing bias or that hallucinate can come at a high cost to customers' privacy, data rights, and trust. Let's first discuss machine learning, which is more explicitly used as a means to extract knowledge from data through simpler methods such as decision trees or linear regression. Machine learning, when set up correctly, helps you make predictions that minimize the errors that arise from merely guessing. For example, companies like Amazon use machine learning to recommend products to a specific customer based on what they've looked at and bought before. Overall, machine learning depends on human intervention to allow the computer system to identify patterns, learn, perform specific tasks, and provide accurate results. Next up is deep learning that uses the more advanced methods found in artificial neural networks. Deep learning requires less human intervention, as features of a dataset are extracted automatically, versus simpler machine learning techniques that often required an engineer to manually identify features and classifiers of the data and adjust the algorithm accordingly. In a nutshell, deep learning can learn from its own errors, while machine learning needs a human to intervene. Deep learning can ingest unstructured data in its raw form, for example, text and images, and it can automatically determine the set of features. That capability is exciting as we explore the use of unstructured data further, particularly since over 80% of an organization's data is estimated to be unstructured. Enterprises generally use deep learning for more complex tasks like virtual assistants or fraud detection. Additionally, deep learning also requires much more data than machine learning, which in turn requires significantly more computational power. Machine learning can typically be done with servers running CPUs, while deep learning often requires more robust chips such as GPUs. Neural networks are made up of a node of layers as mentioned before. An input layer, one or more hidden layers, and an output layer. Each node is an artificial neuron that connects to the next, and each has a weight and threshold value. When one node's output is above the threshold value, that node is activated and sends its data to the network's next layer. If it's below the threshold, no data passes along. Training data teach neural networks and help improve their accuracy over time. Once the learning algorithms are fine-tuned, they become powerful computer science and AI tools because they allow us to quickly classify and cluster data. Using neural networks, speech and image recognition tasks can happen in minutes instead of hours they take when done manually. Google's search algorithm is a well-known example of a neural network. And most deep neural networks are feed-forward, meaning they only flow in one direction from input to output. However, you can also train your model through backpropagation, meaning moving in the opposite direction from output to input. Backpropagation allows us to calculate and attribute the error that is associated with each neuron, allowing us to adjust and fit the algorithm appropriately. Now that we've covered machine learning, deep learning, and neural networks in the first section, let's uncover our second section, which involves natural language processing and large language models. Natural language processing, or NLP, encompasses a suite of algorithms to understand, manipulate, and generate human language. Since its inception in the 1950s, NLP has evolved to analyze textual relationships. It uses part of speech tagging, named entity recognition, and sentiment analysis methods. NLP facilitates machine understanding and engagement with human language in meaningful ways. It can be used for applications from spell checking and autocorrection to chatbots and voice assistants. Natural language processing relies on various processes to enable computers to produce human language. These processes include parsing, semantic analysis, sentiment analysis, speech recognition, natural language generation, machine translation, named entity recognition, text classification, and categorization. Let's discuss each of these natural language processing methods in more detail. First, parsing is a technique that dissects a sentence into its grammatical elements. It simplifies the language structure for machines and aids in recognizing parts of speech, sentence limits, and syntactic connections. Second, semantic analysis advances beyond simple word identification to grasp the meanings and relationships among words. It's vital for interpreting the context of texts, idioms, and humors. Third, sentiment analysis is often used in monitoring social media and managing brand reputation. It evaluates the emotional tone of texts and analyzes customer feedback and market trends. Fourth is speech recognition that transforms spoken words into written text, enabling audio transcription into a readable format. Fifth is natural language generation, which, contrary to speech recognition, provides text that mimics humans' writing based on computer data. Applications include report writing, summarizing, and drafting messages. Sixth is machine translation, which enables the conversion of text or speech from one language to another. Next up is named entity recognition, which detects and classifies essential information in texts, such as names, individuals, places, and organizations. And lastly is text classification and categorization. This functionality assigns labels to text to facilitate sorting and management of vast data volumes, which is useful for organizing documents, emails, and online content. Now, despite the progresses that NLP has made, natural language processing encounters several hurdles that, if addressed, could refine its accuracy and integration into technology. These hurdles encompass contextual understanding, language diversity, ambiguity in language, data quality and availability, computational resources, and real-time processing. Let's discuss each further. Contextual understanding involves grasping language nuances such as sarcasm or idiomatic expressions, which remain challenging, leading to misunderstandings. Language diversity covers the sheer number of languages and dialects, each with its grammar and syntax, which poses significant difficulties. Third is the ambiguity in language, which can complicate the interpretation of NLP systems. Next up is data quality and availability. Because the performance of NLP systems is contingent on the quality and volume of training data, and biases in this data can result in skewed outcomes. The fifth challenge is computational resources, because the demand for substantial computational power for advanced applications limits their development and deployment. Lastly, Achieving real-time processing for applications like simultaneous translation and customer service presents serious technological hardships. If you think natural language processing systems are complex, then you'll be blown away by the scale and breadth of large language models, or LLMs, which offer a comprehensive approach to language tasks. LLMs exhibit fluency and adaptability far beyond traditional natural language processing systems, and large language models utilize a sophisticated tech stack for generative AI, enabling them to 1. Generate content and contextually appropriate text, 2. Engage in meaningful conversations, and 3. Provide answers to questions and create content that closely resembles human writing. LLMs have a few core technologies that allow them to have such a sophisticated foundation. Deep learning allows LLMs to autonomously learn and make decisions using neural networks with multiple layers. The architecture of transformers used in LLMs are designed for handling sequential data and enabling accurate predictions of the next word in a sentence. Self-attention mechanisms allow LLMs to produce more relevant responses by assessing the significance of each word. Lastly, the scalability of LLM's capabilities can be enhanced by training them with progressively larger datasets. Overall, these core technologies have led to various practical applications of LLMs, which include content creation, customer service, language translation, educational tools, and healthcare assistance. Despite the power of LLMs, they aren't without challenges and ethical considerations limiting their technological advancement. The first challenge surrounds bias and fairness because LLMs learn from pre-existing data, which raises concerns over fairness and representation. The accuracy and reliability of LLMs have also been called into question, as the outputs may sometimes reflect data patterns rather than factual correctness, often leading to inaccuracies or nonsensical responses. A third harsh reality is the lack of true understanding that LLMs showcase. LLMs simulate comprehension but lack genuine understanding, thus resulting in errors or inappropriate outputs in complex scenarios. Data privacy is another barrier based on the volume of sensitive data that LLMs handle, which underscores the importance of stringent data governance. The last challenge surrounds energy consumption due to the significant computational resources which pose environmental and resource allocation concerns. Overall, there are 3 pivotal differences between natural language processing and large language models. From a performance metric standpoint, NLP demonstrates high accuracy in specialized tasks, such as syntax parsing and entity recognition, whereas LLMs excel at generating human-like text and managing a wide spectrum of language tasks. From a scalability and efficiency standpoint, NLPs are more efficient at executing specific tasks with lower computational demands compared to LLMs, which are highly scalable and adept at undertaking diverse tasks, albeit requiring greater computational resources. Lastly, from a reliability and scalability standpoint, NLPs exhibit high accuracy and reliability within specialized domains, but may face challenges in tasks that require a rich understanding of context, compared with LLMs that achieve reliability in producing coherent language output, but may also generate inaccurate or biased content influenced by its training data. Both NLPs and LLMs, used in harmony together, exhibiting their strong suits, is what's needed to advance the future success of this technology. The last software section we will cover today involves generative AI versus agentic AI. Generative AI is all about creation. Think of it as the imaginative side of artificial intelligence. These systems are designed to produce content such as text, images, music, code, and even video. At its core, generative AI learns from existing data and uses that knowledge to generate new, original outputs that mimic human creativity. The rise of tools like ChatGPT, DALL.E, and Midjourney has catapulted generative AI into the mainstream. These systems rely on advanced machine learning models, particularly neural networks, to analyze and replicate patterns in the data they are trained on. But generative AI isn't perfect. Its outputs are only as good as the data it's trained on, and if you feed it biased or incomplete data, it will reflect those flaws. Moreover, it doesn't truly understand the content it creates, because it's simply predicting what might come next based on patterns it has seen before. While generative AI focuses on creating, agentic AI is all about doing. This type of AI is designed to act autonomously to achieve specific goals. Agentic AI systems don't just generate outputs, they make decisions, take actions, and adapt to changing environments. Think of agentic AI as the brains behind autonomous vehicles, robotic process automation, or smart assistants that can schedule your meetings and order your groceries. These systems are equipped with sensors, algorithms, and actuators that enable them to perceive their environment, process information, and execute actions. What sets agentic AI apart is its ability to act with purpose. It's not just reacting to input, but considering objectives and making choices to achieve them. For instance, an autonomous drone delivering packages must navigate obstacles, optimize its route, and adapt to unforeseen circumstances, all without human intervention. Generative AI is largely static. It produces outputs based on data it has learned, but doesn't adapt in real time or interact dynamically with the world. It operates within predefined boundaries. In contrast, agentic AI is dynamic. It's constantly processing new information, learning from its environment, and adjusting its actions accordingly. Another key distinction lies in the complexity of their objectives. Generative AI typically works on tasks that are narrow and well-defined, such as generating a paragraph of text or a digital painting. Agentic AI, on the other hand, often tackles broader, multi-step goals that require continuous decision-making and adaptation. Despite their differences, generative AI and agentic AI aren't mutually exclusive. In fact, they often work together in powerful ways. Consider a virtual customer service agent. The agentic AI handles the real-time interaction, making decisions based on user input and guiding the conversation. Meanwhile, a generative AI component could craft nuanced and personalized responses to specific questions. This synergy is also evident in areas like robotics. Imagine a robot chef equipped with both generative and agentic AI. The generative AI could devise new recipes based on user preferences and available ingredients, while the agentic AI handles the actual cooking process, ensuring everything is prepared to perfection. Advances in technology could lead to systems that seamlessly integrate creation and action, combining the best of both worlds. Imagine an AI that not only generates innovative ideas, but also implements them autonomously, which is a game changer for industries ranging from healthcare to manufacturing. The use cases for generative AI are numerous. Businesses are using generative AI to produce large volumes of SEO-optimized content, such as blogs and landing pages that help drive organic traffic. For instance, digital marketing agencies use generative AI tools to create high-quality, keyword-optimized blog posts or web pages for their clients to rank higher on search engines. Marketing and sales is another domain, as sales teams oftentimes are bogged down with administrative tasks when their main goal is to find and develop sales leads. Sales teams have been a generative AI use case for a while now through chatbots and virtual assistants, and the AI technology can do specific tasks and drive optimization on a sales team, along with lead generation outreach. Product design and development is another use case, as the available generative AI capabilities can help organizations in creating new product concepts or designs based on market research, trends, and user performance, which might in turn speed up the product development cycle. An example is a fashion company using generative AI to design a new clothing line and generating designs based on consumer input and market data analysis. Customer support automation is another example, where generative AI can help companies automatically generate responses for customer service inquiries. These tools can craft answers for common questions and troubleshoot issues in real time. Take an e-commerce business, for instance. It can use generative AI in chatbots to handle many tasks, such as order status inquiries, refund requests, and shipping questions. A final use case of generative AI is deepfake technology. While mildly entertaining, generative AI has invented a hyper-realistic image or video by using AI that appears real. It has and is raising ethical concerns surrounding misinformation. Agentic AI is also starting to plant its roots across many industries such as financial services, robotics, city planning, human resources, healthcare, customer service, and workflow management. From a financial services perspective, agentic AI has the potential to revolutionize trading strategies by analyzing market data and expediting the time it takes to execute trades. The extended reach of agentic AI is a significant benefit, as agentic AI can be designed to search the web extensively, and agents are able to retrieve updates and obtain real-time information. From a robotics perspective, places like Amazon warehouses have started to employ robots in fulfillment centers to streamline warehouse automation and manufacturing processes. Next up is city planning, where agentic AI systems in urban planning can analyze all types of datasets to help planners make more informed decisions, such as real-time traffic data and camera sensors. From a human resources perspective, agentic AI used for human resources can help organizations go beyond AI capabilities, and instead provide autonomous decision-making and dynamic employee support. AI agents can automate routine work and provide personalized responses to employees, giving HR professionals more time to deal with their strategic priorities. From a healthcare point of view, a potential use case example comes from Propeller Health, which is integrating agentic AI into its smart inhaler technology. The smart device is collecting real-time data from the patient on medication usage and outside factors like air quality. The device in turn alerts healthcare providers when necessary and tracks patient patterns. Last up is the automated workflow management. Agentic AI can manage business processes autonomously and handle complex tasks, like reordering supplies and optimizing supply chain operations. Another example arises from a logistics company that might also use an agentic AI system to automatically adjust delivery routes and schedules based on real-time traffic conditions and shipment priorities. I want to thank everyone who made it to the end of this video. Today, we covered the history of AI, the top current companies contributing to the expansive AI landscape, and the myriad of software capabilities powering AI's innovation. I hope you learned a lot in this two-part series on artificial intelligence, and as always, please like and subscribe for more great content. Thanks.